Hello everyone. Today our class will continue on section 2, sample space and event. After that, we are going to start section 3, axioms of probability. So now let's review some sample space and event concept we did last time. We consider several examples with uncertain outcomes, right? Uncertain outcomes. Now, what is the sample space? Sample space is a set consists of all the possible outcomes for an experiment and denoted by S, right? Capital letter S. What is the event? Event is any subset of the sample space is known as event. And we know how to define the event for some examples, right? That's some notes we did last time. And we discussed the relation between two events, union, right? Or we read E or F, E union F. That means the outcomes, it consists all the outcomes that are either in E or in F or in both E and F, right? So if it's showing up, if it occurs in any one of these events, it should be included in the E or F. Now, next one will be the intersection. Okay, intersection. Intersection, you write EF or you read E and F. That is the outcomes consist of all outcomes that are both in E and in F. Right? That is the relation between two events, union and intersection. Now, if we have more than two events, okay, more than two events, E1, E2 until infinity, this is the union, this is the notation, union of all the events. That means that consists of the outcome occurs in either one of them, okay. If an outcome occurs in any one of them, then that should be included in this union, infinity union. That is the union of event. And the next one is the intersection. Intersection of infinity event. This index n starting from 1 to infinity, right? So this one consists of the outcomes that is in every en, okay, in every event. Then it comes in this intersection. So the first one, union, means in anyone, if the outcomes occurs in any one of the events, that should be included in this union. But this one should be the outcomes that occurs in every event EI, okay? Outcomes which occurs in every event EI. So they are different, okay? One is union, one is the intersection. And we also talk about the complement. The complement of the event, that means the outcomes in the sample space, but not in the event E, right? All the outcomes in sample space, but not in event E. Actually, that means we can divide the sample space into two parts. The event E or the event E's complement. And E's complement is also called an event, okay? So we did some examples, right? We did some examples. Now, let's continue here, okay? Let's continue here. Subset. Subset. What is the subset? Here, if we have this symbol, okay? If we have this symbol, we read E belongs to F, okay? Or E is contained in F. E belongs to F. E is contained in F. And this side means E is a subset of F. Okay, E is a subset of F. That means the outcomes in all the outcomes in event E, that is also contained in event F. So if we comparing the outcomes in event E and F, of course the number of outcomes in event F will be greater, right? The number of outcomes in event F will be greater than E. E is just a subset, okay? Subset. Here somehow we should combine the concept or the idea from the set theory, okay, from the set theory to this those kind of definition. And we know those symbols, those symbols we mentioned here is the event, right? Is the event consists of the outcomes. And we have already discussed for those kind of event, we can list the outcomes, right? We can list all the outcomes, or we can write it as some description, right? We can write it as some description, like the example we discussed, tossing, flipping a coin, flipping two coins, right? Flipping two coins. So if we have, for example, okay, for example here, let me just use one example, and it's still the example we used before. That's example 2, okay? Example 2. So let's recall example 2. That is still tossing two coins. Tossing two coins. Flipping two coins. Let me write flipping two coins. Let's repeat this example, okay? Flipping two coins, and then we have the sample space, right? We have the sample space. Use the appropriate notation to represent the outcomes, okay? Two coins, so of course we have two times two. Totally we have 4 different outcomes, right? How to represent each outcomes? We put a parenthesis, right? We have both head, and we have the first one is head, second one is tails, HT in parentheses, and the first one is the tail. The second one is head or double tail, right? We put each outcomes in a small parentheses, and to including all the outcomes, we use a curly bracket here. Now, I can define my event E, okay? I can define my event E. I'm going to describe use word and ask someone to denote by to list the outcomes, okay? My event E here should be two head occurs. Let me call my event F first, okay? Let me call my event F first. Or I can write as A, okay? I can write at A. I define my event A. Those are the, we just let those event A is at least, I just use capital letter A. At least one head occurs. How can we represent the outcomes? How can we list all the outcomes? I'm going to randomly select someone to answer it. At least one head occurs. Let's call someone. 26, join the class. Very good. Emika, are you available? You can either reply as Danmu, just plus your nickname, Emika, or you reply in a group. At least one head occurs. How can we list all the outcomes? Not available? Emika. Anyone else can answer the question? How can we list the outcomes in the event A? At least one head occurs. Okay, very good. We get from Emika. Okay. So here, and his notation is perfect. Okay, use a curly bracket to denote all the combination, and each one, okay, each one use parentheses. So at least one head, we have two head, and one head can be HT or TH, right? Very good, thanks. So that is my event A, right? That is my event A. And then I'm going to define my event. I'm going to define my event B. Event B will be 2 head occurs. It's pretty easy, right? 2 head occurs. What is the outcome for event B? 2 head occurs. So my event B will be 2 head occurs, of course, HH, right? Double H, okay? Double H. Now we can see that actually the outcome in B, the outcome in event B will be included in event A, so we can call that B is contained in event A, right? So B is a subset, right? B is a subset of event A, right? Event B is a subset of event A. Be careful here. Those capital letters all means the event. They are not individual outcomes. Okay, they are called event. What is the event? Event is the subset of the sample space. You can only have one outcome. You can only have one outcome. And the one I saw in the group, Luffy did. Okay, Luffy did. He write just HH. That is not a notation for the event. Okay, be careful here. If you write event B is HH, this is not really formal notation. Okay, this is not really formal notation. If you only put the one in parentheses, that means the outcomes. Okay, that means outcomes. This one means you denote by event. Okay, event B. And of course, we can have several different subsets for event A, right? You can define some other event, like event E. The first column is head, the second column is tail. That is also event E. Event E is also the subset of A, right? You can give a lot of definition. You can give another definitions of the event, which is subset of event A. Make sense? So here we just list one examples. Okay, and again for the event, you should know how to describe it. Use those words or list all the outcomes. And by the way, here the event A and event B we are talking about here, they are all subset of sample space. There is no doubt, right? Any event we list here, any event we list or define here, they are all subset of the sample space. There is no problem. Sample space lists all the possible outcomes for this experiment, right? Make sense? So here event A and B are subset, right? That is some example we showed for the subset. Okay, for the subset. Now we are going to talk about the graphical representation of the event. Some relation between two events or more than two events. And this one is called the Venn diagram. Okay, Venn diagram. And it's very common in the set theory. Venn. V-E-N-N, double N. Venn diagram. Venn diagrams. It's the graphical representation. Now here in those kind of graph, okay, in those kind of graph, here the rectangle, okay, here the rectangle, the full rectangle box represent my sample space. Rectangle box represent the sample space S. Okay, and each circle represents the event. Okay, each circle represents the event. So of course you will see here the sample space, this is a box, and any event we are talking about should be included, right? Should be included in the sample space inside the rectangular box, which means it's a subset, right? Any event is a subset. Now the first one, let's look at the first one. If we have two events, okay, if we have two events, E and F, the union, E union F or E or F we called. So that will be this shaded region, and that is what we said should be the outcomes either in E or in F or in both E and F, right? Should be the shaded one. You might ask, if there is no intersection for E and F, how about if there is no intersection? So you just shaded two circles, right? You just shaded two separate circles if there is no intersection for the number 3 part. So that means the outcomes either in E or either in F. It doesn't matter. But here, if they have some overlap, that is the part we call the 3. Both the outcomes both in E and F, right? That is E union F, the graphical representation. And E intersect F, E and F. E and F consist of all the outcomes are both in E and in F, right? Both in E and in F, of course, should be the intersection here, right? Should be this intersection, both E and F. For example, as we said, if we have the separate two circles, E and F, I think my circle are kind of perfect. Okay, let me change a different color. So if we have two events, E and F are in this way, okay, then if we have E and F are in this way, what is E union F? That's what I said. Should be all the outcomes in E or in F. So here there is no part 3, there is no intersection. So should be shaded region of those two circles, right? That is E union F, E or F. But in this diagram, what is the E and F? What is E and F? Let me just use this kind of color. So what is E and F for the graph I'm talking about? If E and F are separate two circles, comparing with here, there is no intersection, right? There is no intersection, which means there is no common outcomes, right? There is no common outcomes, or there is no outcomes existed both in E and F. Yes, it's called the null event. How can we represent the null event? This one, right? It's similar like the notation. It's the same notation like the empty set. How can we call the E and F in this way? What is the name for the relation what is the terminology to describe the event E and F if E and F are null event? What is the terminology to describe? Null event are not enough to answer this question. We should know more about the relation between this kind of case. E and F are called mutually exclusive. Okay, exclusive. We should understand more concepts in the probability part, okay, than doing the calculations. Okay, mutually exclusive. So that is the case. I list the two circles in this way. They are separate one. Okay, they are separate one. Those two events, E and F, are called mutually exclusive. Now, part C. Let's look at part C here. So if we have the event E, what is E? E's complement. E's complement is also the event. That should be all the outcomes in the sample space, but not in E, right? So we should shade it all the part except the circle, right? Except the circle. So that is E's complement. Okay, that is E's complement. By the way, what is E and E complement? What is this one? E and E's complement. E is the circle. E's complement is all the other part except the circle. Of course, this is still the null event, right? And this is important relation. E and E's complement, they are, how can we call the relation? How can we call it? Mutually exclusive, right? And this is true. Think about it. This is true for all the event and its complement. For any event in the sample space, this event and its complement, they are always mutually exclusive to each other, right? Any circle you join inside the in the box, that means any event you define here, its complement, the event and its complement, they are mutually exclusive. This is the important way we are going to do the division of the sample space. Okay, that's why we should get familiar with the mutually exclusive, right? And especially here, what is E union? What is E union? E's complement. E's complement is the part outside of the circle. What is E? E is inside the circle. What is the union? Union means you combine all those outcomes. Of course, the union should be the sample space, right? The union of those two. E or E's complement equals sample space. Those two are very important. Okay, and that special concept between one event and its complement. The intersection of one event and its complement, they are null event. They are null event. The union of the event and its complement, they consist the sample space. Okay, they consist of the sample space. Now, the subset. Okay, part D sample space. Okay, this is sorry. Part D is the subset. So F is the subset of the sample space. No problem. F is a circle, right? F is a circle in the rectangular box. Then E is called a subset of the F. Of course, E should be a circle inside the F. Okay, inside the F. And some special case. Okay, some special case. If we have E is a subset of F, and F is also a subset of E, even E is a subset of F, and F is and F is also a subset of E, then we will say E equals F. Those two events, they are exactly the same. They consist exactly the same outcomes, right? If we have those two special relations. If E is a subset of F, F is also a subset of E, then those two events will be exactly the same. Okay, so be careful here. The E and F we are talking about are event. Okay, are event. So that's the graphical representation, and let's check more the rules of event. Okay, the rules of event. This is very sim. This is the same. Actually, this is the same as the set operations, right? This is the set of operations. So rules of event, commutative laws, E or F, that is the same as F or E. No problem, right? No problem. If you use the Venn diagram, it's easy to check. The order does not matter, right? The order does not matter. E and F equals F and E. No problem. They consist the same number, the same set of the outcomes, right? Now let's check associative laws. Okay, associative laws. E union F, then union G. So so this one means you do the operation inside. You find the result. You find the outcomes for the event in union F first, and then union G. Okay, then union G. So that is the same as you find the outcomes in F union G, and then union the event E. It doesn't matter actually, right? It doesn't matter which one goes first. It's what does those mean? What does those mean? So this one actually equals E union F union G. Sorry, E union F union, not belongs to. Okay, not belongs to. So what is the union of three events? What is the outcome gives for the union of three events? E union F union G. That will be the outcomes either occurs in event A, event F, event G, or in any intersection of any two of those events, or in those three events, right? Here are three. Now, here E and F, then and G. That will be F and G first, then and E. That will be the outcomes occurs in every event. E, F, G, right? E, F, G will consist of the outcomes in every event. E, F, G. This one implies the union of three events that will occurs in any event E or F or G. This one means the outcomes occurs in every event. Okay, so they are different. Okay, they are different associative laws. It doesn't matter about the order. Now, a little more complicated is the distributive laws. Okay, distributive laws. E union F intersect G. Okay, event E or event F and event G. So that equals the operation will be E and G union F and G. Okay, here EEG means E and G, E and G union F and G. Now the second one, E and F, then union G. So that will be E union E or G and F or G. This two parentheses, between two parentheses, that implies and. Okay, that implies and. It's a distributive laws. It's similar like you have A plus B times C, right? It's similar to the rules of algebra actually. Similar, okay? Similar to this kind of distributive laws. If you have A plus B times C candle, right? Similar, just we call similar, equals AC plus BC, like that, right? It's very similar like these laws. We are going to use the Venn diagram to show the distributive laws, okay? To show the first one. Now we are going to show E or F and G. How can we write this one? Distributive laws. E or F and G. That will be E and G union F and G. Right? Let's use the graph to show that. So let's take EG. If we have three events, E, F, G. Okay, E, F, G. This, if we put the overlap for those three events, that is more complicated. Okay, that is more complicated. You can have three circles inside the sample space. They are totally separate. That will be easy to figure out, actually. Right? We just give the common case if they all have the overlaps. Okay, if all those three events have the overlaps. So here, E and G, we are doing the part on the right side. E and G, okay? E and G, that is E and G shaded this intersection, right? Shaded the intersection of the circle E and the circle G, right? And then what is the F and G? F and G is the same, the intersection of the two circle F and G, right? F and G. Now, those two parts, A and B, part A and part B, we will do the union, right? We will do the union, which means combine all the outcomes in those two parts together. So we will shade it both, right? We're going to shade it both. So this part actually represented the right side, EG union FG, right? EG union FG. So EG union FG, that is this part. That is this part. How can we understand? How can we understand this part is the same as E union FG? Let me show you, okay? How can we understand this part is the right side, is the left side, okay? Not perfect. So this is E, F, circle G. Now let me choose a different color. Do this part, okay? Do this part. So the left side, let's look at the left part. E union F. E or F should be all those orange part. All those orange part. We should shade the both circle E and F, right? E and F. That is E union F. E or F. So those orange part, E union F and G, that means intersect with G, right? This part intersect with G. What is the part intersect with G? Should be this part. Now let me choose a different color. Let's do black. Okay, let's do black. So this union part intersect G, so that will be intersect the circle with G here, right? So should be this part, that is the left part. That is E union F, and then intersect G if we use the graphical representation, right? So this black part, okay, this black part is the E union F, E or F and G, right? This is black part. So that is the part here, right? That is the part here. They are the same, right? They are the same. And what does this part mean from part A and part B? And we know this part is E and G, or E and F and G, right? So that makes sense, right? That makes sense. And it will be very obvious, or it will be a direct way use the graphical representation. And also you can try the second one, the second part of distributive laws to draw that. And especially you might have the case like you have even E and F, they have intersection, or you have G like this one, okay? It doesn't matter, okay? It doesn't matter. You can list several different relation between the three events E, F, G. You might get some null event. For example, here this one. If you have E, F, G like this, so what is your E, G? Of course, there is no intersection with E and G, so the event E and G will be the null event, right? You can have three separate circles, right? You can have three separate circles. We just give a more complicated case to show the distributive laws, okay? Distributive laws. Now, let's check some common rules, okay? Common rules we call the De Morgan's laws. This part is also common in the set theory. Okay, in the set theory. Now let's try to understand those two. The first one means we have the union of an event, right? We have the union of an event, complement. The union of an event, E2 until En, its complement, that will be the intersection. That will be the intersection of each event. Each event Ei's complement will be the intersection of each event's complement. How can we prove this identity is true? Let me just give you some clue, okay, or some idea how to prove this one, okay, how to prove this one. Usually we are going to suppose any x from the left side, which means any element, okay. Here we know actually the x means the outcomes. The element in this subset is the outcomes, but just in the set theory we usually use x. Any event, any element we choose x from the left side, then we can prove that this x belongs to the right side, okay. This element belongs to the right side. That is the first part we prove. What does this mean? What does this mean? Any element you choose from the left side, then it belongs to the right side, which means this way, which means the left set is the subset of the right side, okay. This is the first part. This one is the subset of the right one. That is what is implies. We choose any element x that belongs to the right side. And then the second part, you choose any x again, or any other notation, any y, it doesn't matter. You choose any x from the right side, the intersection of Ei's complement, then you can prove this x belongs to the left side, okay, belongs to the left side, which is the union of all the n event, then take the complement. So in this way, part two means you prove the right side, the right part is the subset of the left side. So that is what we said. E is a subset of F. F is a subset of E. What does those two subsets implies? E and F, they are the same event. E equals F. That is the idea how we prove it. And in our textbook, they give some explanation. Okay, if you are interested, you can read this part in the textbook. And here, the second one, okay, the second one, it's the same idea to prove that. You choose any x from this one. You choose any x from the left side, then that belongs to the right side. This is also a set, okay? This is also the, not set actually, this is the event, okay? This is the event we call, okay? It's a event. And then if you choose any outcomes, any element x from the right side, that belongs to the left part event. Then we prove those two events, those notation, they are the same, okay. They still denote the event, okay, event. And especially here, if we take n equals 2, this is the case, okay, when n equals 2. When n equals 2, it's easier to understand, okay. When n equals 2, so we have two events, okay, we have two event union, right? Two event union, E or F. We have two events, which means E1, E2, just two events. You can also represent as E or F. It doesn't matter you use E1, E2, or E and EF, okay, those notations, it doesn't matter. So two events, E or F's complement, that equals here. What does this one mean? This one means E's complement and F's complement, right? E's complement and F's complement. Second one, when I is 2, so that will be the intersection of two events, E and F, then take the complement. That equals E's complement union F's complement, right? If event F's complement. So it's very clear to figure out when n equals 2 or when n equals 3. It's easy to understand that. Okay, it's easy to understand that. Let me just list one of those. Okay, let me just list one of those. Let's check this one. If we choose any x belongs to E union F's complement. Okay, E union, think about it. If you choose any x, any element, here the x represents the any outcomes actually. Any outcomes belongs E or F's complement. Think about the Venn diagram. So this x is neither in E or neither in F, right? The E union F will be the part we shaded the circle E and the circle F. So its complement will take the part inside the rectangular box, but except those two circles. So that means X should be the outside of the circle E, and the element should be the outside of the circle F. Then what does this mean? X is in the E's complement, which is in the outside of the circle E, of the event E. And then X is also outside of the circle F. So it's in both parts. The X is in both complement, both event complement. Of course, X belongs to the intersection of those two events, right? So in this way, we prove that any outcomes we choose from the E union F, that is the idea we follow here. Okay, that is the idea we follow here. Sorry, an eraser. Let me finish here. Okay, then we can take the break. So here, E union F, the left side, E union F's complement, that will be a subset of the right part. Okay, that will be a subset of the right part. Then how can we do another part? We choose any x contained in the right side. Okay, this is a right side event. So this is E's complement, and in F's complement, which means X is in E's complement. And because here means the intersection, X is in E's complement, X is in F's complement, right? X is in F's complement. That is the one we did, right? X is in both complement, right? X is in both complement. So X here, X is in the outside. X is in the outside of E's complement. So X does not belongs to here. This symbol means not belongs. Okay, not belongs E union F. Right? X does not belongs to E union F, because X is in E's complement and F's complement, which means the outside of the circle E, outside of the circle F. So if you have the E union F, you are going to shade the two circles together. So X is outside. X is outside of those. What does X is outside of those two circles? Which means X is outside of the circle, which means it's complement. Right? Which means it's complement. So that implies we prove the right side, the right side event is the subset of the left part, okay, the left side event. So here we have the relation I mentioned before, okay, I mentioned before. Let me choose a different color. So here we prove that the left event is the subset of the right one. And also we prove the right side is the event. The right side event is a subset of the left side. What does those implies? This implies those two events, they are exactly the same. So it's easy to prove when we have n equals 2. When we have n equals 2. And this one, we can also follow those kind of analysis to prove this identity. And it's the same idea, but maybe a little more complicated to prove the case when we have n event, okay, when we have n event. And in this course, in the probability and statistics course, students are required to prove some simple identities, okay. So here those stuff does not require you calculate anything. It's different from the topic, the calculus or our linear algebra. It does not require you calculate anything, but you should understand the logic or understand the probability concept, then you are able to prove it, okay. So now we are done with the section 2, okay. We are done with the section 2. Then we are going to start the section 3 after 5 minutes break. Now let's take a break.